Hello there, I'm Yamin Afifi, and in this presentation, I will be talking about the application of MOSFETs and EMG signal conditioning for a myoelectric prosthetic hand. Hello there, I'm Yamin Afifi. So, what are myoelectric prosthetic hands? A myoelectric prosthetic hand is basically an artificial limb. This artificial limb uses electrical activity from the person's muscles as a control signal. When a person, for example, contracts a muscle in the forearm or any residual limb, the muscle produces a small electrical signal. These signals can be detected from the surface of the skin using EMG electrodes. The prosthetic system does not use the raw muscle signal directly. Instead, this signal is first processed by an electronic circuit. After processing, the signal is converted into a command for the prosthetic hand. For example, if the person contracts one muscle group, the hand may close, and if another muscle group contracts, the hand may open. This makes myoelectric prosthetic control important because it allows the person to control the artificial limb using their own biological muscles rather than using a manual switch or a button. So, we've been speaking about EMG. What is an EMG? EMG stands for electromyography. It is a measurement of electrical activity produced by skeletal muscles. When a motor neuron activates muscle fibers, small electrical potentials are generated. These potentials spread out through the muscle tissue and it can be detected at the surface of the skin using an electrode. In this application, the EMG signals act as the biological input to the prosthetic control system. Surface EMG has several important features. It is non invasive because the electrodes are placed on the skin rather than under the skin. It reflects muscle activation, meaning it tells us when the muscle is active. However, this signal is usually small in amplitude and is easily affected by noise, motion, and electrode placement. So, the key idea is that the EMG contains useful information about the muscle contraction but is not clean or strong enough to be used directly. So, now let's talk about why we can't just take normal raw EMG signals and directly use them. We cannot use them because it's weak, noisy, and unstable. The prosthetic motor requires a clear electric command, but the signal detected from the skin is a biological signal with many unwanted components. One issue is that the EMG signals has a small amplitude, so it must be amplified before it can be processed properly. Another issue is noise. Movement of the electrode on the skin can create motion artifacts. Power line interference from electrical equipment can also affect the signal. In addition, the signal can change depending on the skin contact, sweat, and electrode placement. This is why signal conditioning is needed. The purpose of signal conditioning is to amplify the useful EMG signal, reduce unwanted noise, and prepare the signal for digital processing. In simple terms, a circuit changes raw EMG into a more stable and usable control signal. So, we spoke about why EMG signals are not fit. Let's talk about how we process them. So, the full electronic signal chain of processing starts from the muscle contraction all the way to the prosthetic movement. So, the process starts with muscle contraction. The muscle contracts, surface EMG electrodes detect the small voltage produced by the muscle activity. Then the signal goes into something we call an input protection and basing stage. This helps protect the circuit and prepare the input signal. After that, the signal enters the MOSFET or CMOS instrumentation amplifier. This is one of the most important stages because it amplifies the weak voltage difference between the electrodes. Then the signal passes through a bandpass filter. The purpose of this filter is to keep useful EMG frequency range while reducing unwanted low frequency and high frequency noise. After the filtering, the signal goes through rectification and envelope detection. This helps convert the EMG waveform into a smoother signal that represents the overall muscle activation level. Then the analog signal is sent to an ADC, analog to digital converter. The ADC converts the signal into digital values that can be processed by a microcontroller. The microcontroller then decides what command should be sent to the prosthetic hand. Finally, the driver provides enough power to move the prosthetic actuator. In this chain, the MOSFETs are important in several parts of this. especially in the instrumentation amplifier, active filters, ADC, and the microcontroller circuits. Before explaining why MOSFETs are suitable for EMG signal conditioning, it is useful to compare the three transistor types BJT, FET, and MOSFETs. A BJT, or a bipolar junction transistor, is a current controlled device, has three terminals, base, collector, and emitter. A base current controls a large current flowing between the collector and the emitter. This makes BJTs useful for amplification and switching. On the other hand, FETs, or field effect transistor, is different because it's a voltage controlled transistor. It has three main terminals: gate, drain, and source. The voltage applied to the gate controls the current flowing between the drain and the source. Since the gate draws very little current, FETs usually have high input impedance. And lastly, MOSFETs is a type of FET with an insulated gate. It has a gate, drain, source, and body terminals. The gate voltage controls the channel through an oxide layer. MOSFETs are widely used in CMOS integrated circuits. So the key difference is that BJTs is controlled by current, while FETs and MOSFETs are controlled by voltage. The MOSFET is especially important because its insulated gate gives it very high input impedance and makes it suitable for more modern integrated circuits. So why does MOSFET fit better for EMG signal conditioning? For EMG signal conditioning, the signal input comes from the body through surface electrodes. Since this signal is weak, the input circuit must not draw too much current from it or load the signal. A PGT can provide good amplification, but it requires base current. This is less ideal for weak biomedical signals because the input stage may load the electrode signal. FAT is better because it's voltage controlled and it has a high input impedance. However, the MOSFET is the most practical choice because it combines voltage control, extremely small gate current, very high input impedance, low power consumption, and excellent integration in CMOS circuits. This is especially important for wearable prosthetic systems because they need to be small, low power, and battery operated. So the final comparison is a PGT can amplify well, but needs to input current. A FAT is better for weak signals because it is voltage controlled. A MOSFET is the best practical choice because it combines high input impedance, low power, and seamless integration. So, what is the MOSFET role in the EMG analog front end? So, let's talk about the analog front end first. It is the first electronic stage that receives the signal from the electrodes. This stage is very important because, as we said before, EMG signals are still very weak and they're very sensitive to noise. If the first stage is not designed properly, the signal can be distorted before it's even processed. The main jobs of the analog front end are to receive the weak differential EMG signals, avoid loading the electrodes, amplify the voltage difference between the two electrodes, reject common mode noise, and prepare the signal for filtering and digital conversion. So, MOSFETs are suitable here because MOSFET input stages have very high input impedance. This means they draw very little current from the electrodes. This matters because the electrode skin interface can have relatively high impedance. If the amplifier input impedance is too low, the EMG signal may become reduced or distorted. The key idea is that the MOSFET allows the circuit to sense the EMG signal voltage without significantly disturbing it. So, here we're talking about an example circuit for the CMOS differential amplifier. This can be used to explain the first amplification stage of an EMG frontend. The electrodes provide two input voltages, voltage in positive and voltage in negative. The purpose of the amplifier is to increase the difference between these two input signals. In this circuit, M1 and M2 form the input differential pair. M3 and M4 act as an active load or a current emitter. M5 acts as the tail current source. The output is the amplified signal here. When the voltage in positive becomes slightly higher than the voltage in negative, the current through one side of the differential pair changes. This current change is then converted into a voltage change at the output. The important point is that the amplifier responds mainly to differences between the two inputs. This helps reject common mode noise, which is noise that appears on both electrode wires at the same time. This is useful in EMG systems because many interference sources act or affect both electrodes. The differential amplifier helps keep the useful EMG differences and reduce shared noise. So the function of this circuit is to amplify the useful EMG differences while rejecting common mode noise. So after the amplification process, it is still needed to be filtered. The signal is still not filtered. The purpose of filtering is to keep the useful muscle activity and remove the unwanted signal components. A typical conditioning chain includes an amplifier, high pass filter, low pass filter, an optional notch filter, a rectifier, and an envelope detector, and then, of course, the analog to digital converter. The high pass filter removes slow changes in the signal. These slow changes may come from electrode movement, baseline drift, or motion artifact. The low pass filter removes high frequency noise that is not useful for prosthetic control. A notch filter may also be used to reduce 50 Hz or 60 Hz power line interference. After filtering, the rectifier converts the EMG waveform into positive values. Then the envelope detector smooths the rectified signal so that it represents the overall muscle activation level. The MOSFET connection is that in integrated biomedical electronics, these active amplifier and filter stages are commonly implemented using CMOS circuits. This means MOSFETs form the internal active device used to process the signal. So now that the EMG signal has been amplified and filtered, we send it to an ADC. The ADC converts the analog EMG signal into digital values that can be processed by a microcontroller. A simple prosthetic control system can use threshold control. For example, if the EMG level is low, prosthetic hand remains at rest. If the flexor muscle EMG is high, the prosthetic hand closes. If the extensor muscle EMG is high, the prosthetic hand opens, sorry. More advanced systems can classify different EMG patterns. This allows the prosthetic hand to recognize different intended movements, such as grip, pinch, wrist, rotation, or release. The microcontroller usually does not power the motor directly. Instead, it sends a control signal to a motor driver circuit. MOSFETs can also be used in the motor driver stage because they can efficiently switch higher currents to control the prosthetic actuator. So, in this final stage, the conditioned EMG signal becomes a digital decision, and that decision becomes a prosthetic movement. So, now let's talk about the importance. This application is important because it connects the human nervous muscular system to an artificial limb. The user does not need to press a button to move the prosthetic hand. Instead, the remaining muscles become the biological control interface. There are several biomedical advantages to this. First, it supports more natural control of prosthetic movement. Secondly, it allows the user's own muscles activity to become the input signal. Third, it enables wearable and portable prosthetic systems. Fourth, it reduces the need for large external electronics. Finally, it supports future development of smarter prosthetic control systems, including systems that use machine learning. From an engineering point of view, this application shows how electronic devices are directly used in biomedical engineering. The MOSFET is not only a theoretical component from electronics. In this system, it becomes part of a circuit that allows biological signals to be measured, processed, converted into functional movements. So, finally, the EMG signals are weak and noisy so that they cannot directly control a prosthetic hand. MOSFET based circuits help solve this by amplifying and filtering the signal before it's processed by the microcontroller. MOSFETs are suitable because they have high input impedance, low power consumption, and strong compatibility with CMOS integrated circuits. Overall, MOSFET signal conditioning helps transform weak muscle activity into useful prosthetic control commands. Thank you.